Yeah, yeah.
Hello everyone, very good morning to you all. Thanks for joining this presentation. I am Bsmillah Kani. I am an AA intern in Cellstrat AA lab. And today I'll be presenting you a method called Grad-CAM, which is more related to the bigger topic like explainable AI. What Vivek give a brief introduction before this presentation. The crux of this paper is tries to answer this question, why your model predict a particular class, and we tries to give an explanation for that prediction. So we will dive into the topic and we will go into the details. So this is my content of today's presentation. I will start with the introduction and then we will go into the main topic of Grad-CAM and different aspects, how it works and what are the uses and such like that. And then we will see some applications where this Grad-CAM can be used, and followed by how this Grad-CAM can be implemented. And finally, I will share you a collab notebook where there is a code demo. You can run through it and see it in action. Okay, a little bit background of an AI, especially the deep learning in computer vision. As you are all aware that in last decade, we have achieved some great breakthrough performance in many tasks like image classification and object detection. This is possible only after the technique of deep learning came possible in the field of computer vision. So if you have some background in computer vision, probably you might already be aware that it was the task like image classification was like it was not giving the accuracy that we had. But once we had this deep learning, it gives tremendous improvement in the performance. Yeah, although we achieved a great breakthrough, but the downside of this deep tech is that it is very difficult to interpret like what it is exactly doing. Unlike the classical machine learning where you try to hand features every steps of the machine learning pipeline, so you have an inherent intuition of what exactly the model is doing. But deep learning is like you give a data and you give you the target, and it tries to figure out the method itself. One way it is good, but on the downside, as I told you, it was very difficult to understand, and it remains to be a black box for most of us, right? Um yes, so now in recent years, the interpretability of the model becomes a topic. When you present your deep learning model to a user or a business stakeholder, it is always very difficult to explain him like why your model is working in such way. So the interpretability becomes a question, and there is always a notion that um, there is always a compromise on accuracy for interpretability. So if you see, like many actually try to prefer a simple classic machine learning model, and then they compromise on the accuracies because simply because that the model is more interpretable and explainable to a business user. But it is not necessarily true that we should compromise accuracy just for the sake of interpretability. uh, so we can find some technique that it has both interpretable and also you don't lose the accuracy. uh, okay, why we need such interpretable explanation for the benefit of AI evolution? So there are the usefulness of such interpretability uh, can be classified into three stages of AI. right? So this so let's say you have a stage where AI is much weaker than humans. For example, tasks such as visual questioning answer, where humans easily outperform any machine learning or deep learning models. But what these interpretable techniques helps for AI researcher is that it will helps to identify why the model fails, and he can then focus on improving the models on an area which the model fails. That is one use of such interpretability. And let's say another stage where AI is in equal performance with humans. So the tasks such as image classification, right? The ImageNet task. So any CNN based architecture model can classify an image on in a performance and on par with humans, right? But the problem is that you do not understand why the model predict a dog or cat, and it is very difficult to build a trust for a business user on such models. And especially it is very sensitive on specific domains such as healthcare. For example, chest x-ray diagnosis. These are like very sensitive areas where you have to build trust on healthcare professionals like radiologists and doctors, and they have to trust this model. Yes, the AI model is working correctly, and it is not predicting, and it is predicting a particular disease with a lot of sense. Another stage where we will be going is that AI becomes much more stronger than humans. For example, in games like chess and Go, AlphaGo, maybe you're aware of it, where the AI machines defeat humans. But what do we get from a benefit from such interpretive model is that using these techniques, you can then ask the machine to teach those techniques to humans, which they use to defeat the humans. So then humans can learn from the machines, and they can use it in their task, right? That is one of the use, if you can see. And what makes a good visual explanation actually? So when you develop interpretation for any CNN based models, it should have two distinct features. Like, one, it should be class discriminative, which means that it should be able to localize the category in the image. For example, if you have an image with a dog, and the model should look into the area of the image where actually the dog is, and then give you the predict the correct classes dog. So that is class discriminative. Another thing is it should not only be class discriminative and localization, but it should also be high resolution, which means that it will give you the fine details of those areas where where the model looked into it. For example, if you are classifying a cat, and it not only tells you as a cat, but it also tells you what is the breed of cat. For telling the breed of cat, then it looks into the fine details of the features in that particular cat image. Probably there are some stripes in the cats, like that. So these are the two things that we will keep in mind, and we will see how the Grad-CAM tries to achieve these two goals. So Grad-CAM, as I explained to you, is a technique to explain the AI model that you are deploying it. So Grad-CAM stands for gradient weighted class activation mapping. This is a technique that visually explains your model, or are particularly only CNN based models. So this does not apply for other NLP uh, uh, or other architectures. It's purely based on it's purely applicable only for CNN based models. And it will try to understand, or it will show you what parts of the image that influence the model to make a particular decisions. We will see in coming slides like what it actually is mean. And the good part of Grad-CAM is that it is very easy to implement, and it is very intuitive, and it gives you a lot of other benefits that we will be seeing in coming slides. uh, as I explained to you before, it achieves the two goals of what is a good visual explanation of a model is. So it is class discriminative, and also it gives you a localized visualization, and also it gives you finer details as well. So before we dive into Grad-CAM and how it works and what are the max behind it, probably we will take a minute or two to actually recall what are the CNN basics. Probably some of you might not be fully aware of what is a CNN based model. So CNN is actually stands for convolution neural network. And what is a convolution operation is what is shown here. So this is a given an input image which has nh number of rows and number of columns, and then you do a convolution operation on this image using a convolution filter. And what it does is that you place this filter on top of this image, and you do a element wise multiplication and then sum it up and put it into the pixel here. So these are the filter values and these are the image pixel values. This is how the element wise multiplication is done, and they have been summed up and they'll be put into this picture. Okay, so there are many other details like what is the filter size and number of filters and what stride it has to use, whether to do padding or not. All these things are that, but we will not go into those details now. So this is one simple convolution operation. So what it is, an input image, you do a convolution operation, and what it result is actually we call it as a feature map. So 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 this is where the Grad-CAM will operate on, right? And yeah, this is one convolution operation, and then we build a CNN architecture with this operation as basics. And you can add any number of layers, like if a deep neural CNN neural network will have almost like 200 layers. So here I'm just showing you some only 3 layers. It's a very simple CNN architecture. So you take an image and then you convolve it using a filter size of 3 with 10 filters, I suppose. Yeah, and then you get an image size of 37 cross 37 into 10, because you're using a 10 filters. And then you do a subsequent operate convolutions, and then the image is being downsampled and downsampled, and finally this is your feature map, which is 7 cross 7 into 40. And this feature map is then flattened into one single dimensional vector. So 7 into 7 into 40 results in 2960 feature maps. And then you do a softmax operation on this, and then whichever the class which has the highest probability is your predicted class. So this is the basic, and it is important to understand this if you're not having a CNN background, so that you will understand how Grad-CAM is applied to give an explanation of why this particular model predicted this particular class. So I see some questions coming up. Yes, so is the matrix multiplication correct? This is not a matrix multiplication. Okay, I don't know. I lost my question. So this is an element-wise multiplication. So it's a dot product. Okay, so moving on. So now we come into the main technique, Grad-CAM. So this is the overall architecture of the Grad-CAM. Uh, uh, so what it says, what it does is that given an input image, you pass the input image through the CNN architecture, and it calculates the feature maps. And once you have the feature maps, you can do uh, uh, any task based on this features map, right? If it is a simple image classification, then you do a flatten of these feature maps into fully connected layers, and then you do the softmax activation, and then you predict your class whether it's a tiger cat or not. Or you can use these feature maps and passes through an RNN or LSTM architecture, and you can try to do an image captioning task. Or you can use these feature maps and do a visual questioning answering task. So now I will just explain you the Grad-CAM using the image classification task. Okay, so but the Grad-CAM, the advantage of Grad-CAM is that it is not restricted to only one type of architecture. So you can use any off-the-shelf CNN architectures and also use it for any CNN-based task. Okay, so the steps are that you have an image and you pass through it, and what it will do is that it will forward propagate the image through the CNN of the model, and then through the task specification, and obtain you a score for that particular class. Once you have this score for this, and this is the score for tiger cat. So what you do is this is where the Grad-CAM operation starts. You make that particular class as 1 and remaining to be 0, and then you do a, a back propagation. So that is what is explained here. The gradients are all set to 0 for all the class except the decide class, and then the signal is back propagated to the convolution feature maps. Okay, and uh, I'm just annoyed by this. Okay, and then uh, yeah, the signal is back propagated to the rectified convolution feature map of interest. Okay, and then what it does is that this is the gradients, and this is the weights of that we then we multiply it with the weights and then apply a ReLU, and that will result you in a heat map. So we will see the equations behind it, and then that will explain you better. So there's one question now. What is the use case of Grad-CAM? Any other algorithm which is similar to Grad-CAM? What is the okay? So the use case of Grad-CAM is to give an interpretability of the model. That is the main task of Grad-CAM. But there are some use cases that we will be seeing in the coming slides that will answer your question. What are the similar methods to Grad-CAM? That also we will see. There is one method called CAM. Actually, that is where it started. But there is a limitation of CAM. So CAM is just a class activation mapping. So we will see what are the limitation of CAM and how Grad-CAM solves those limitation of CAM. And can you please let us how this is different from normal convnet image classification? So this is not an another CNN architecture to do an image classification. No, this is a method that will try to give you an visual explanation of any CNN architecture for your image classification task. So you can take any CNN architecture like ResNet, VGG, or EfficientNet. Okay, uh, but the thing is that these CNN architectures are very complex that you sometimes do not understand, and it remains to be a black box, like why the model predicted a image as a cat or dog. So this Grad-CAM can be applied on your CNN architecture, and it will give you an visual explanation of your model prediction. uh, okay. How to know desired class in a completely new set of image. uh, so the desired class is what is your class of interest. So let's say when you have a simple dog versus cat classification, so you can tell Grad-CAM, can you give me a visual explanation for dog? Then it will show you a heat map that will show you why a model will predict that image as a dog. Or if you say, can you give an explanation for a class cat, then the Grad-CAM will show you an visual explanation why the model will predict this image to be a cat class. At default, the Grad-CAM will use the class which has the highest probability, but it not only restricts there. So you can ask an explanation for any class actually. So for example, the ImageNet 1000 class task, there are some 1000 classes are there. So by default, you can just ask for an explanation of the class which has the highest probability, but it not only is that possible, but you can ask for explanation for any class actually.
Yeah, Bismillah, I
um,
didn't understand the guided backprop and the rectified convolutional feature maps. What is meant? What is these rectified maps?
so rectified is just a ReLU rectified linear unit. That is what it is mentioned here. So there is no any specific or any architecture modification is there. It is the same ResNet architecture where you have rectified convolution units, right? So that is where the future maps are there, right? So you have a convolution operation, and then you apply a ReLU activation. So that is what is your future maps. So the Grad-CAM will be applied on there actually. So that is why they have
So,
mentioned.
what is guided backpropagation? What is meant by guided backpropagation?
Yeah, I will explain you that. So guided backpropagation is only yeah, this backward in the backward propagation, right? So that is the backward propagation. But guided back propagation means that you say that you give me the back propagation for this class. So you are not telling to do a back propagation for without any restrictions, but no, we are restricting the back propagation for a particular class. So if it is a dog, then the backward propagations or the gradients are calculated only for that particular class. So which means it will give you the gradients and activations only for that class actually. So that is why it is called guided back propagation.
So, regular backprop is still in action through the
Yes,
regular
yes.
convolutional network, and you have a second stream of backpropagation only for the relevant class of interest.
Yes, only for the relevant class of interest. That's why it's called guided propagation. So this Grad-CAM is not involved in your training process or prediction process. So you can use your ResNet or any CNN architecture to do training on your particular data set, and you can do a prediction. But this Grad-CAM is applied after the prediction. Okay, and then it will give you an visual explanation of why this model predicted this image to be a dog or cat. So for that, you have to tell, okay, you predicted this image to be a dog. Can you explain me why you predicted this to be a dog? Then you say that okay, then my yc will become, only for the dog class I will make it 1, remaining all I will make it 0. So then when you do a back propagation, the feature maps or the neurons, whichever been activated for that particular class will be visualized later.
So you seem to be taking the heat map from the intermediate convolutional layers in the middle stream, and that heat map, that colored blue screen, you are multiplying dot product with the guided back propagation. You are doing dot product of or element wise multiplication of those two images, and to get
Yes.
guided Grad-CAM. Okay.
Yeah. So this is called Grad-CAM actually. So Grad-CAM is just an visual heat map. So in this we are predicting it to be a tiger cat. So when you do these Grad-CAM operations, so it will produce a heat map like this. So in this image you see that the tiger cat is being highlighted here. But the thing is that I told you there are two features for an explanation. One, it has to do class discrimination and localization. Okay, another, it should also tell you the finer details why the model predicted it. So here you can see it gives you a localization of highlighting the cat region, but here it is not, the fine details are not visible. So for that what we do is we do a back propagation, get the gradients, and then you do a element wise multiplication with the Grad-CAM, then you get a guided Grad-CAM, which will give you not only class discriminative and localized, but it will also give you a finer details of it. So we will see in coming slides what is the max behind it. So probably that will explain. So I see a lot of questions. How can we infer here? Okay. Yes, backpropagation is only for the decide class. How it works with multiple class? Yeah, you can do multi-class image classification. As I told you, ImageNet 1000, it has 1,000 classification, 1,000 class, and you can ask an visual explanation for any class you want. So in this image, it is a dog cat. So you can ask an explanation for dog, or you can ask an explanation for cat. Are you going to explain how Grad-CAM or Go creates heat maps and how it different from occlusion sensitivity? Yes, I will try to explain that. Okay, I think that's all the questions. So this is the, you compute the gradient of that particular class with respect to the feature map activations. And what you do is once you have this gradient, you do a global average pooling. Okay, and that gives you the weights importance or the neuron importance. And then what you do is you just multiply these weights with the actual future map activations and apply a relu, and that will give you a Grad-CAM. So it's a very 3 simple steps you can do. I will explain you again. So you have a score for all your classes, and you select which class you want an explanation, and you compute the gradients of that particular class with respect to the future map activations, and you get a gradient, and then you do a global average pooling of that gradient that will give you an weights, Okay, and then if you multiply these weights into the actual feature map activations and apply a ReLU, that will give you your actual Grad-CAM. Why is the logits of that particular class? Yes, correct. I think we can. Okay, as I told you, this is a simple technique. So these are the main things. Please elaborate on gap, where I mentioned gap. Okay, gap is just nothing, an average operation, right? It's computing a mean. So what will for example, if you see one of the layers in the SNet, in the last layers, it will give you an future map of the dimension uh, of 1 comma 7 comma 7 into the number of layers, like 4096, right? So what we'll do is, once you do an average pooling of this, and then it will take the mean of those in the final dimensions. So it will give you an weights that is actually can be multiplied just element wise with the activation maps. So it's just an average. Maybe when you see the code, probably you will understand.
See, Bismillah, normally we have dj over dw, right? D of loss function with respect to d of weights. So
Yeah,
derivative of loss function with respect to weights. So here I don't have the loss function in numerator. I have the YC class, and
yeah,
in the denominator I have the activation maps, which are convolutional activation maps instead of the weights per se. So dy
yeah,
over dA versus d of loss over dw, I am trying to differentiate or understand. Uh,
yeah.
so
For
normally when we
example,
say gradient, it is a d of loss over d of w.
no, we are not
Uh,
we are not calculating gradient for the loss, but we are calculating gradient of the logits, right? The class,
okay,
the class of your interest with respect to the activation maps. So if you do a backward propagation in your CNN, so here you will get y class. So now we have to, if you actually in PyTorch, if you do you do a backward operation, then you will find the gradients, right, with respect to these feature maps. For example, this is my feature map, the last layer. What is the gradient of this class with respect to these feature maps that I can get?
correct, correct. So that is y minus y dash or mean square error divided by d of w for that layer. But now you are doing d of logits of y are divided by d of that layer values.
This one, yeah, correct.
So it is
And
a
then
different kind of gradient. It's not the usual loss gradient.
no.
Okay.
um yeah, and then we do an just an simple average operations, and then we multiply, that will give you the weights. And then if you multiply the weights with your actual activation map, and that will give you the Grad-CAM. Yeah, when you see the code, probably you can understand. Actually, it's simple to implement, but please elaborate. Can you show an architecture diagram where the pooling is happening, if it is there? Mm, okay, actually, I'm sorry. In architecture, it is not shown. Actually, as I told you, This is where the weights are calculated. So here it is not shown here, but they only shown you the weights into the activation maps multiplication, and then apply a ReLU function. What exactly are the future map activation? Are the values of concourse after the activation function? Yes, correct.
See, normally loss gradient is rate of change of loss with respect to rate of change of weights in different layers. Now here we are saying rate of change of the logits y with respect to the rate of change of the class activation values, the convolutional values a, which is capital A. So it's dy over dA instead of dl over dw. So we are calculating the rate of change of output logits with respect to the convolutional
Activation map.
layer. Yeah.
Yeah, yeah.
So
After
are we
you
going to
apply
try to minimize that? Are we going to try to
no, no, no,
minimize
no.
that?
There is no minimization, nothing. So
So
it's
that's
only
the
an
other
operation.
difference. Here you want minimize that new kind of gradient.
Yeah, minimization means you are training, right? There is no training. That is
Right,
also an
right.
advantage because some of the explanation you have to do retraining. You have to try to minimize those errors. But here there is no need of any minimization or retraining.
Right.
So it's just a simple three-step operation actually. But what you get out of it is really very useful.
So this is tracking the rate of change of y logits with respect to the convolutional activation maps A, and you are doing global average pooling over all the intermediate convolutional layers. So that's what is global average pooling. You are summing it up and averaging it, and then you are multiplying that rate of change alpha with the
Mm.
activation map itself, and
Yeah,
taking a ReLU on top of that, which will eliminate negative values and preserve positive values
exactly,
only.
exactly. Yeah.
So
Why
why are we
ReLU?
doing
It is
alpha
because
into A? What is alpha into A going to do? Alpha into A
yeah.
will
So we have the activation maps from the last layer or any layer you want, but I am giving a weight only for this particular class. So this is the weight
right.
of my future map K for this particular class C. But this activation is a general activation map. So what I'm trying to do by multiplying this is that I will highlight the regions of this
Hmm,
particular class,
hmm.
okay, and then I will minimize the other regions. So finally I will get a heat map out of it.
I got it. So basically, you are alpha into A means that you are saying the which convolutional activation map is contributing to that class determination alpha.
Class,
So
yes,
alpha is the weight. So we are weighting the
weight, yeah,
convolutional maps, and you are saying that which of the convolutional maps. So you are weighting the convolutional maps. So if alpha is
yes,
small, that means that particular capital A has in less effect, and if alpha is
mm,
large, so that particular convolutional activation map has more effect on the determination of y. Okay, yeah, I understand now. Okay.
mm, yeah, X. Okay, I think that is about a cam. Now we will see some more aspects of how gram is Grad-CAM can be useful. But before that, maybe it is good to compare CAM and Grad-CAM, right? Because CAM is what came before Grad-CAM, and why Grad-CAM is better than CAM. We will try to understand here. So CAM is also will give you an activation maps like what I shown before, but the limitation of CAM is that it requires a specific architecture. Like it can be applied only for one type of architecture, where you have the penultimate layer before your this should be a global average pooling. Okay, so it cannot be applied to an CNN architecture where you have a fully connected layer. Okay, And so this is a mandatory step for class activation map technique. And since this is an mandatory requirement for a class activation map, what will happen is that then you cannot do you cannot build a model which can give a more accurate predictions, but for the sake of interpretability you try to compromise the accuracy. But Grad-CAM uh, does not do that. So you can take any off the shelf CNN architectures and you can apply Grad-CAM. Okay, 1 moment.
No, you said fully convolutional layer cannot exist.
For CAM, fully connected layer.
Fully connected layer cannot exist. I mean, that exists, right, for image classification or any image task.
Yes, that exists. That exists for RESTnet, for VGG. Yes, it is exists. But for CAM, you have to modify that architecture. So you have to remove all the fully connected, and you have to put a global average pooling on that. And because doing that, your model accuracy goes down. But since you want a interpretability of such getting such heat maps, you compromise your model accuracy, and then you give an explanation. So why you should compromise and give an explanation? Grad-CAM, you don't have to do any modification, you don't have to do any retraining, you just have your any CNN architectures and you can get such activation maps.
So you are saying in CAM you have to do it. In Grad-CAM you don't have to remove FC layer.
No, no need.
Okay. So you are saying CAM was a previous solution for the same thing, but
Yes.
Grad-CAM is a more modern solution for the same thing.
Yes, so Grad-CAM is a generalization of CAM,
Okay.
and it can be applied to also CAM can be applied only for image classification task, a dog, is cat, or whatever. But it cannot be applied for an image captioning task or a visual question answer task. No, it cannot be done. So Grad-CAM, you can take any CNN architecture and also any image task, image based task. There's one more question. I'm sorry, I'm just losing track of. Yeah, this seems to be simple and very elegant. Yeah, that is the good thing about Grad-CAM. So just to like few lines of code you can do it, but only but it gives you a lot of benefit actually. So that we will see in like what benefits you can get out of it. Okay, so then let's proceed. Oops. Okay, yeah, if interested we can just get into some max here. Okay, why would they say that Grad-CAM generalizes CAM? Okay, as I told you that in CAM you need a global average pooling before your class. Okay, and this is what is done. So you have your final layer feature map. Okay, and then you have to do a global average pooling, and then your whatever the weights will give you what class it is, right? So this is an easy equation. So this is the CAM equation. So what we will do is we will take this and we will see how we can generalize this uh, 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 this activations. So for that we will say that the future map FK to be that just again a global average of the activation map of layer K, and then what CAM does is that it applies the weights WCK over these feature maps, and it gives you the class prediction. And what we'll do is we will take the gradient of this previous equation, so dy by df. Okay, so in similar to what we shown in that in the Grad-CAM. And okay, so this is how the equation is that. And then what we will do is from equation 2 in the previous slide, so yeah, okay, what I'm doing here, one moment, dy by df. I think I made a mistake here. No, it's okay. Dy by df. Okay. Okay, so the future map, so that df by dA in equation 2, like df by dA is actually 1 by z, right? So you can substitute 1 by z in the denominator here, and we get this equation. Okay, and we take a partial derivative in equation 3 with respect to fk. Okay, so dy by df then again becomes wck. Okay, so this becomes a wck into z into dy by dA, and then we do sum over all pixels, so sum over ij of the weights, sum over ij of the gradients, and this is z is nothing but the total number of feature map pixels. So this is nothing but z, so it becomes z w o c k, and you can rearrange it and you will get like this. So finally the weights of that feature map k of that particular class C is given by the sum over the gradient of that y for that particular class C with respect to that activation map k. So if you see, this equation is exactly the same as the Grad-CAM equation, right? Only that there is an constant called 1 by z. So if you see, uh, yeah, if you see this activation, this weights alpha ck is exactly the same as wck here. So here they prove that this is identical to Grad-CAM equation. So thus the Grad-CAM is a generalization of CAM. Uh, yeah, I think this just for those people who are interested to know a little more max. But yeah, it is not really important that whether we should understand this, but it is good to know. Okay, now we will see, like a lot of people were asking how Grad-CAM can be used. Before that, there is one question. Image segmentation object detection can also be used to segment object classes in an image. So in case of image segmentation, is Grad-CAM helpful? That this helps in image classification example. In image segmentation, what I will show you and how Grad-CAM can be used in image segmentation in a moment. Okay, so as I told you, Grad-CAM is class discriminative and also localize the model prediction. Okay, so but it lacks the ability to visualize the fine-grained details. So far, whatever I explained you in the previous equation, I told you like how to compute Grad-CAM, but it will give you only a heat map with the coarse localization. But what we can do further is that there is a technique called guided Grad-CAM. What we will they do is that they compute guided backpropagation, and they compute Grad-CAM, which is a heat map. And if you do a element wise multiplication of this guided backpropagation and Grad-CAM, what you will get is guided Grad-CAM. which is not only localize your predictions, but it will also give you a finer details of those localization. I'm not sure whether you can see the image with quite good details. Actually, if this is the original image, and if you do a guided back propagation, so we get fine details, but the problem is that it is not localized. So we are actually trying to get an explanation for an cat prediction. So in this you see there are fine details, but the details are all over. There is no any localization. And as I explained you, the heat map or the Grad-CAM, it gives you a localization explanation, but we can combine these both two, and you see the only the cat is highlighted here and the dog is not highlighted anymore. But it also not only localizes, but it also gives you the fine grain details of those cat. For example, it is highlighting the stripes of the cat. So with this you can not only tell this image to be a cat, but you can also tell this to be a tiger cat, because it has stripes, which is an unique feature for a tiger cat. That's called a guided Grad-CAM. Guided Grad-CAM is nice. Does it work well in a crowded picture or video with multiple cats sitting, standing, sleeping near each other? I think you're touching on another topic, which is actually multiple occurrence of the same class. As you told, maybe it is possible in a crowded picture where you'll have like 4-5 cats. There is one more paper called Grad-CAM plus plus, which today we will touch upon. And so they claim that it will solve those multiple occurrence of same class. We will see how they are doing it. So as yeah, it is in the coming slides. We will see that. So this is guided Grad-CAM, and now we will see some applications or some usage of Grad-CAM. Okay, so Grad-CAM can be used for a couple of use purposes, especially for AI researchers. They want to when they are developing a new architecture. So this can be a very handy tool to understand their models better. So one application what they claim in the paper is called a counterfactual explanation. Okay, so just by just negating the gradients in the weight equation, so you can get an explanation uh, for your model prediction for the opposite class, right? So this can be it can be useful. Yeah, I'm not sure. I've not used this counterfactual explanation, but probably if someone wants to explore this, they can use this. So it means in your Grad-CAM implementation, you can just simply negate your equation and it will give you the explanation for the opposite class. So in this example, this is an original image, and what is a cat counterfactual explanation is that it will highlight the dog, and for a dog counterfactual is it will highlight the cat. Okay, another use that they claim in that paper is that Grad-CAM can be used for weakly supervised localization. So take for example the task of ImageNet localization challenge. So in this challenge of the goal is not only to predict a particular class, but you should also give a boundary box of that particular class. So if it is having a dog or cat, So you should not only tell why the it should not only predict what class it is, but it should also give a bounding box. But how can we use Grad-CAM to achieve that? So what we will do is that, given an image, we first obtain what class it is, and then what we will do is we will generate a Grad-CAM. So it will give you a heat map, and it will give you highlight the region where that particular class is there. Then what you can do, you can do a simple image segmentation. How the image segmentation is done is just by a simple thresholding. So you take your heat map, and then you apply a threshold by 50% of your maximum intensity as a threshold. Okay, then you will get some fully connected blobs of regions, right? If you're aware of what image segmentation does. And then what you do is you take the biggest connected segment, and you can draw a bounding box out of it, right? It's a very simple technique. So you don't have to do full-fledged training with some annotated bounding box. So if you want an object detection with the bounding box, so you can have an simple ResNet architecture. You will give you an image prediction, dog or cat, and then you apply the Grad-CAM, take the heat map, do a image segmentation on the heat map, and put a bounding box around the dog or cat. So it will be cool actually. So they do some analysis of the ImageNet localization challenge. So they compared the top 1 and top 5 metrics. So they compare it with the state of the art image localization architectures. So as you can see, the Grad-CAM is performing on par with or sometimes better than the state of the art techniques actually. So with just some simple techniques, you can also achieve without big training or a big specific architecture. So this is an added advantage of that. Okay. So this is weakly supervised localization. And as one of you asked, like how can we use this use for segmentation? So as I told you, so Grad-CAMs gives you a heat map. So what you can do is that this is also an technique, right? So for image segmentation, so this is the ground truth, and this is your input image. Now you have to get the silhouette of this bike, right? So what you can do is you can just apply an a Grad-CAM on this, and it might give you an heat map. And what you can do is you can use this Grad-CAM as a seed for your image segmentation. So what is a seed? For example, if you're aware of watershed segmentation, right? So what watershed segmentation does is that it will try to create a seed, and it will expand the boundary from that seed, and until an watershed region is being found. So it tries to build a dam actually around that object. So in watershed segmentation also, the seed that the process starts is very sensitive. If you start with the wrong seed, you end up with the wrong segmentation. But how do we find the correct seed for that segmentation? So why can't we use Grad-CAM for that? So Grad-CAM will give you a heat map. You do some small coarse segmentation and use that seed and apply your segmentation. Oops. So what they do is that they compared, even CAM was used for such segmentation, and then they compared the intersection of union score for CAM and Grad-CAM, and you can see there is quite a good improvement over the CAM actually. So you can use Grad-CAM for your segmentation also. And and we will see some other applications using Grad-CAM. So I will explain you three things: analyzing the failure modes actually, and I'll show you an example of how an effect of adversarial noise can be explained through Grad-CAM, and also how to identify bias in the dataset. Now, when you are building an image classification model and you have a lot of classes and your accuracy is not so great, now you have to uh, now you have to deep dive into understand why the model fails. So what tools you have to uh, uh, to explain these models? So you Grad-CAM is one such tool that can be very handy to explain. Take for example these four images. So this is actually an volcano image. I'm still not sure whether you can see the details of it. Actually, the real class is actually a volcano, but the model predicted it to be a sandbar. For this image, the real class is actually again a volcano, but the model predicted it to be a car mirror. And in this case, the real class is a beaker, which is shown here actually, but the model predicted it to be syringe. And in this, it's actually a coil pipes, but the model predicted it to be a snake. So what we'll do is you can actually get an Grad-CAM visualization of the actual class, which is volcano, and also you can get a Grad-CAM visualization of the predicted class, which is actually wrongly predicted, which is a sandbar. So I'm still not sure whether you can see it. So what happens is that in the volcano, this volcano or the mountain is highlighted here. But in our model predictions for this sandbar regions are highlighted. So it is very clear that yes, our model actually looked into this particular region and it predicted to be a sandbar. So what problem is there in this image data set is that there is a lot of ambiguities are there, whether to tell this image as a volcano or tell these two images as sandbar. It can be tell both. So whether to tell this an image as a volcano which is seen inside an car mirror, so whether tell this a car mirror or volcano, we don't know. So here you have both, you have a beaker, you have syringe. So which one to tell, we don't know. So this looks also like a snake, right? So we don't know which to tell. So the model actually predicted a snake, thinking that this looks like a snake, and that's what it explains here. But due to the ambiguity of the image itself, the model gives you a wrong prediction. So how to proceed this? Probably you should kick off this such kind of ambiguous images out of your data set. Because sometimes what we do is we assume our data set is perfect, and then we do a lot of changes in our model. We do a lot of training for hours, and finally we don't go anywhere. So instead we take a pause and then look into why the model predicts this way. And then if it makes sense, yes, it makes sense because the picture looks very ambiguous, then probably you should actually remove these images from your database, right? With this one more question, fine grained makes sense. This manufacturing model is okay, that's actually not a question. Okay, okay. Now another application is how do we try to understand the effect of an adversarial noise. I think there was a popular paper, I think, right, and that's what came as a GAN, right, Ian Goodfellow. So what he said is that our image classification models, um, you just by introducing a small noise into your image, right, the model will give you a completely different predictions, right? So that was that paper was talking about. So now but now you will be clueless like why it looks like this image. This is the original image. And this is an image with a bit of an adversarial noise introduced into it. Actually, there is not much big difference between these two, but the model will predict a completely different class. So in this, it will predict the class to be an airliner with a very high probability. Almost it was 100% confident that this is actually an airliner. So this is what an adversarial effect of an image classification task is. So just by introducing some noise, your model will completely fails. But using Grad-CAM, you can try to see what exactly is going on here. So you can ask for an explanation of that class which you think is correct, and also the class which the model predicted it. So if you ask for an explanation of Grad-CAM for a dog, so the model explains, gives you a highlight here, and for a cat it gives you here. But for an airliner, it was highlighting all the background things. So it gives airliner because probably this activation was very high, and it ended up to be this is the class with high probabilities. Your model activation maps, feature maps, everything is okay, but because of those noises, it activates more and it gives you those particular class actually. So this gives you a nice explanation of your model prediction. And another use is to identify bias in your data set. Yeah. So this is like a gender bias example in your class predictions. For example, take a data set where you want to predict whether that image is a nurse or a doctor. So you say you have some 500 images of nurse which are labeled as nurse, and 500 images which are labeled as doctor. So what the Grad-CAM can identify whether your model is biased or not biased. So if it is a biased model, uh, which is shown here, which actually was not looking into the correct features, it was just looking into the face and a hairstyle, and that it was telling it to be a nurse. But rather, if you see an unbiased model, it will look into the important features which are more related to the nurse category. For example, the half sleeves used here, or the stethoscope, or the white coat which is used, which is being highlighted here. So you should actually prefer a model which is unbiased towards your data set. So if you go into Google and type nurse, you will almost get 90% of your images female images, right? And if you actually type doctor, most of your images will come as male. So this is actually a gender biased data set, or a gender biased model. So if it is a female, it will predict to be a nurse. If it is a male, it will predict to be a doctor. But we want a model which is not biased. So Grad-CAM can try to explain or try to identify a model which is not biased with your data set. So these are some other applications. So as I told you, it is not only restricted for image classification task, but it can be also used for image captioning or visual question and answer. So in this example, they are showing you an image captioning task. So this is an original image, and the model says an caption to be a group of people flying kites on a beach. And why it gave this caption? Because it find some kites, and also it find some people, right? And then it says here a man is sitting at a table with the pizza. So it highlighted the man, and it also highlighted the pizza. And also visual questioning answer, you give an image, you ask the model what color is the fire hydrant, and if it says red, it will highlight you here on the red part of that image. Let's say if the model says yellow, you highlight here, and if it says yellow and red, it means it is highlighting the entire fire hydrant. uh, can Grad-CAM be used to explain other deep learning models like OSIC2? No, as I told you, the Grad-CAM is only for CNN based architectures. not for any other NLP task. I am actually not aware of other techniques. Probably there should be there. I'm not sure actually. So for NLP task, maybe there are some other techniques, but this Grad-CAM is only for CNN based architectures. Okay, so now we will come to the actual coding part of the Grad-CAM. So how do you implement Grad-CAM in code? Yeah, in this session, I will show you using PyTorch. So in PyTorch, there is a functionality called hooks. So using hooks, just with few lines of code, you can implement a Grad-CAM. So hook is just basically a function that is executed during a forward or a backward call. Yeah, using this autograd function. So what you do is you just put a forward hook to your activation maps and also a backward hook. And when you are executing a forward pass or a backward pass, so those values in the activation and gradients will be stored in array, and those array can be used to calculate your Grad-CAM. So it's just a few lines of code, right? You don't have to do all the way back, compute all the gradients again. So it's a very handy tool in PyTorch hooks. Mm, okay, how to write a forward hook and a backward hook? Yeah, how just call this. Yeah, I think it's elegant to put it into a class rather than writing all this one, because you can also, once the hook is not used, it can be removed automatically. So this is the function. So you have your model. So it takes a model, or it particularly it takes a layer of the model, not only the model. So you can pass in any layer of your CNN architecture into this as M, and then a forward hook will be registered into that layer. And when you do a forward port operations, that values will be stored in this, and you can use that for your Grad-CAM calculation. So similarly, you can also do a backward hook. So yeah, it's the same thing. Only thing you have to do a backward here. So here for a forward hook function, it will actually take the layer and input and output. So input is your image, output is your class. For gradient or the backward hook, you will actually give your gradient input and it will give you a gradient output. So that is the difference. Okay, we are almost finishing. Okay, so as was mentioned at the beginning of this presentation, we are actually a part of a product, healthcare product team. We are developing a solution for chest X-ray diagnosis for, especially for COVID-19 patient. And that is where we came up with this idea of Grad-CAM to actually give an explanation of your model. So in this example, I'm showing you an COVID patient chest X-ray, and our model is able to predict this X-ray as a COVID. But it also not only gives you only you the prediction, but it also will give you an explanation of the model why it predicted this X-ray to be a COVID. So as you see in this heat map, the lungs are highlighted here. But there is something else is also going on here. So it also not only highlights the correct region of lungs, but also highlights some anomalies, or how to say out a noise over the top left of the chest image. So there is some text written here. Probably that is not an explanation of why this chest X-ray is to be in COVID patient, but because there is some text is here, that is also highlighted here. So it might be an indicator like, yeah, probably you should do some pre-processing of your chest X-ray and remove those text on the left and the right, and then you do a model prediction, because there might be a possibility that your model will give correct prediction, but it might not be looking at the correct regions. So it is important that you understand why your model predicted this X-ray to be a particular disease, and also it gives you a correct explanation. So when you show this to a radiologist or doctor, and if you do some pre-processing and remove these all these regions, and it shows only the highlights at the correct region, then the trust of the doctor on your model increases, and that will helps to deploy the model into a real life, right? Otherwise it is very difficult to convince a doctor or a radiologist to use your AI model. uh, okay, as I told you, like I will just touch upon another extension of this technique, which is called Grad-CAM++. Yeah, this is essentially the same, but I just found this paper which is actually published from a research team in India. So they took this Grad-CAM and then they extended it. So what they do is they claim that Grad-CAM++ solves two issues of Grad-CAM. One is that it also improves the localization by covering the entire object, but not just a part of an object. um, and also it solves another problem where I mentioned earlier that you can try to get an explanation for a multiple occurrence of the same class. So when you have like 5 dogs, probably Grad-CAM will might highlight only 1 or 2 dogs. The other 2 dogs might not be highlighted, but when you say Grad-CAM++, all 4 dogs will be highlighted. How do they achieve that is that just they replace this weight equation, which is a global average pooling in Grad-CAM by an weighted average of the gradients. Uh, yeah, actually I tried this. I have not noticed a very significant difference with Grad-CAM++. Um, but I would recommend just use Grad-CAM. But it's good to know that there is something called Grad-CAM++. If it is maybe useful for your purpose, maybe you can use this. So it's just a small modification in the weight function, and that will give you a different heat map. But personally I do not see a very big difference in this technique. I think these are the references, the papers, some GitHub repos, some Medium articles I used for this slide, and maybe we can start with the code demo now. I can share you the collab notebook. Any other questions as of now?
Okay, that's great. So any questions, audience, before we proceed with code demo? Really interesting presentation. Okay, maybe we can proceed with code demo. Are you going to share the code, Bismillah?
Yeah, how do we share this code?
You can send this in the chat itself to everyone.
Okay, fine. The modules is I'm using here PyTorch. um so I'm just getting the image. So this is the image that they used in the paper to explain you the one. um and then we do some pre-processing of the image just to resize it into the standard size, convert that into a tensor, and then do a normalization. And you can use any pre-trained model. It is not restricted to any particular type of model. So here I have, for the demonstration purpose, I'm using ResNet. Okay. And uh, okay, so here just for the purpose of understanding, I have taken the ImageNet classes names. and then there's a dictionary of the class index and actual class names. So in this class, the actual class is actually a boxer, which is a type of a dog, and the class index is 243. So this comes out of that ImageNet 1000 class challenge. And it also has another class called cat, which is actually a tiger cat, and this class index is 283. So we will generate Grad-CAM for these two classes and see how that visualization looks. um yeah, as I told you, 243 is a boxer class. Okay, so as I explained to you, you set up PyTorch hooks for the forward pass and the backward pass like this. So here first I will show you how you can implement this by yourself. What are those three steps how you can implement that using PyTorch hooks. But we'll also see some already existing APIs from GitHub. Yeah, which you can if you're not aware of how to implement this by your own, you can use the APIs just out of the self. So here I'm just showing you forward hook and backward hook, and what you do is you initiate the backward hook and the forward hook. And what we are doing is in RESTnet, we are actually getting the Grad-CAM visualization for the layer 4, which is like the final layer. Okay, so here you have to pass the layer for which you want the explanation actually, and the RESTnet will predict the class that is your output. So when you do a forward pass, okay, your activation is stored here. That is what we get activation. You see, you in a simple one line of code, you get your activation. So you do a forward hook, you do a prediction, and those activations are stored here, and that you can get it in a variable. That is for the forward hook. And using a backward hook, what you do, you get the output class. In this, you see, I'm just I want the gradients only for my class of interest. So in this, for my class of interest is the boxer class, which ID is 243. So I do a backward, and those gradients are stored using the hook, and I get the gradients. So I have the gradients, I have the activation maps. So now what I do is I take the gradients and I do a global average pooling, and I will get my weights. And then these weights are multiplied with the activation, right? You see, the weights are multiplied with activation, which means that in this activation map, wherever there is a dog, that will be highlighted and other regions will be suppressed. And I just applied relu, as Vivek explained correctly. It will get rid of the negative values, because in the paper they found that if you don't apply relu, you actually get a 50% less performance, 15% less performance. uh, so as you can see, then you can just overlay the image, the heat map on the original image, and see. So in this class, this is the boxer dog. It highlighted that. Now if you can also do another thing, so now let's say if you want activation map for my cat class, so you can change the class name here. So that actually is, that class name is, okay, I think I made a, so that actually is a tiger cat. So now what I will do is I will get my activation and gradient for that class, which is a tiger class, and then I compute my weights. Then I compute my Grad-CAM, and then I will visualize my Grad-CAM. Oops, I think that the image has changed, so I will run it again. By using the same variable. Apologies, I was using the same name. Okay, so I have to initiate all the variables again. It's not necessary. Okay. And then I wait, compute my weights. I hope it works. Yeah. So for a cat, tiger cat, you see that the cat is activated here. So this will give you a nice explanation of why your class is predicted by the model. So this I explained you just by writing your own code, but there is an API called PyTorch Grad-CAM. So you with that you can just call without any code. So here in this image, this is the heat map. This is actually Grad-CAM. So in this they have also implemented Grad-CAM plus plus. So this is Grad-CAM heat map. This is Grad-CAM plus plus heat map, and you see both are similar results only. I do not see much difference, but what they claimed is that they are able to get multiple occurrence of same class to be better. So using the same API you can do for cat, and this is an example where there's a multiple occurrence of same image, same class. Let's see if Grad-CAM plus plus is better than Grad-CAM. Actually I do not see much difference. Okay, so that's why I told yeah, I'm not very happy with Grad-CAM plus plus, but probably you might get different results for your different task. Yeah, that is about Grad-CAM, and I also showed you about a guided Grad-CAM. Also I'm using a different API. So here it shows you the heat map, and here it shows you the fine grains of that dog, right? So it will so with that you can have a better understanding of why that prediction happens. I think that's it. I think some questions are coming up. I ran it successfully, thanks. Bad audio. Are you able to hear me properly?
Yes, it's fine for me.
Okay. Did you share the link for this code? Sorry, I'm not seeing for some reason. Uh,
I've sent the code just now again. I've sent the code
okay.
again.
Okay. Uh, yeah, I think it's a very simple technique, but it can be really useful for your some of your research, especially if you want to dive into research and want to yeah, also for the business users, especially for healthcare applications, this can be useful.
I think for healthcare it's very important
Mm-hmm.
because the customer is very difficult to please. So it's important to show this additional explainability feature.
Yes, absolutely. Yeah.
So fantastic presentation. Audience, any questions? Okay, any final questions, audience? I hope you were able to run this code. It ran very fast indeed. So Bismillah, should we be using that pre-trained model which we are showing or of Grad-CAM or use the custom model most of the time?
No, you can use any custom model. There is no restriction to use Grad-CAM. So even for our healthcare product, right, COVID, we have a custom model for that.
No,
So
I
in that
meant Grad-CAM API in PyTorch. Should we use Grad-CAM API in PyTorch or the custom code you built for it above that?
Oh, okay. So yeah, you can use this actually. So it's just very simple, right? So you don't have to depend on some external libraries. So we don't know, maybe during production you might end up some issues. So these are some simple implementation with that you can integrate into your code, and it will give you an output like this. I would suggest to go with this.
Okay. In the COVID-19 product, you are using this code, huh?
Yes.
Okay. So this session is being recorded, and it will be available for our Prime members or AI Lab members. So if you are a new guest today, just reach out to us how to become a member of our Prime group or AI Lab group. There's another question here, Bismillah, how this can help in neural architecture search, NES. Uh,
What is neural architecture search?
yeah, that is a optimization design technique to create optimal neural architectures. I don't think this is related to that. That is just optimized neural network design algorithm. So that is different, I think.
Yeah, you can compare different architectures and choose architectures that